Okay, so we are coming up on the end of chapter 3 here. We have this set of slides and one more after that, but the heavy lifting for the chapter was last lesson with that s and r squared stuff. This lesson here is going to get you a chance to practice some of those skills in the context of computer output. So what do I mean by that? When you use statistics, if you're going to do research someday, you're not going to have like a little TI-84 sitting right there where you type all your data into this. You're going to instead use a computer software to do it for you. You aren't going to be calculating your own R by hand and stuff like that. It's going to be where a computer gives you the information. There are a lot of really popular, famous programs that do stuff like this. Minitab is one, JMP is another, SAS. Like there's all these different programs that you can use to do regression. And what the AP test kind of decided for you guys for statistics, it's not reasonable to teach you how to use all these different softwares. It's just not. There's no time for it. That they cost money. It's just not a possibility. But they can have you look at output from those programs. So when you look at these like this box over here, this is what the output looks like when you use the program Minitab. So it shows you the stuff that it would give to you after you type everything in. And the AP test does expect you to be able to interpret one of these things, and they're labeled, but to look at one of these and extract the key pieces of info you need to analyze the problem. I would say this is actually even more common than using your TI like linreg stuff, because when you type stuff in your calculator, it takes a while and it's easy to make a mistake and mistype something. If they give you the computer output, it's helping you for the future if you ever do use this stuff, and everybody is on the same page. There's no danger of typing it in wrong or wasting time on it. So very common thing to be familiar with. And the things you need to be able to find are all written right here. You need to know where the y-intercept, the slope, s, and r squared all are, and it varies depending on the type of program you have. So these pictures here label where the things are found. So I'm not going to talk too much about those right now. The most common one that you see a lot is this kind of output right here. So Minitab output is fairly common on the AP test. There is a bunch of extra stuff over here that will eventually become useful to us. Like we're talking chapter 12 right now, very end of the class. We'll come back and talk about these. But for right now, they don't matter to us too much. So I'm going to this is like chapter 12 over here, the TEP stuff. And we will never use R squared adjusted. That is a multiple regression college level stats thing. So when you look through this stuff, just be aware that you're picking R squared and not R squared adjusted. And if you look over here, they've got in this one R squared adjusted, you would still ignore that. Everything is labeled. You just have to be able to work your way through it. So I'll talk about that when I do our big example for the day on the next slide. All right, so our big problem for the day is looking at where you sit in class, so how close you are to the front board, has an influence or an impact on your score on chapter tests or some sort of like achievement in class. So row 1 is very close to the front, and then row 7 is sitting all the way in the back of the room. And we want to know if how far back you sit will have an influence on how you score in class. So just by using the eyeball test right here, this does not look super convincing. If I got data like this, I'd be kind of like, oh gosh, maybe it's not that big of a deal where I sit, which logically there's a lot more important things than like where you sit in the classroom for how you're going to do on tests. But at the same time, even though this isn't very good, if you look at the residual plot over here, it's randomly scattered. So it's not that like the line is going to do a good job. But what this says is a linear model is like as good as anything. You're not going to find a better model than a line. Okay? And they give us a little computer output here in the middle. The next page, I ask you for a whole bunch of things. Equation for least squares regression line, et cetera, et cetera. So let's talk about how you interpret one of these boxes. When you're looking at these, standard error coefficients, TP stuff, that's later on in the class. R squared adjusted, we will never use. We want regular R squared. So everything you need is right here. When it says coefficients, this is the coefficient for your constants. The constant is your plane number, or in other words, your y-intercept. So on the next page, the first thing they ask for is the equation. You can fill this in there. My y-intercept is right here. And this is the coefficient on rho. Rho is my x variable. So this is a fancy way of saying the coefficient on my x. which is the slope, which is negative 1.1171x. I'm going to put a y equals in front of it for my equation. Make sure you always use y hat when you do this. Now, if I were to just write this, I would not get full credit because I didn't define my variables. You have the option of like putting the words from the problem in here. Like you could go 1.17 times rho, and then I could put for my y hat, this would be like score, but I'm going to put hat on score for predicted score. You can do it this way if you like this better. Or if you like your traditional x and y, you just have to define them. So x is going to be row number, and y hat is the predicted score. So either of these would be an acceptable thing to do, but if you use the x and the y hat, you have to define your variables. Okay, so you just pull that out of the nice little table right here. What else do I ask for? Interpret the slope of the regression line in context. So the slope in this problem was going to be, it was like negative 1.1171x on the end of the equation. This guy is my slope. And remember, you put it over 1. For every 1 unit increase, so for every 1 row further back, for every 1 increase in x, y increases, or in this case, because it's negative, decreases by about negative 1.11. So for every row further back you sit, score is predicted, gotta say predicted or you'll get half credits, to decrease by about 1.1171 points. So that's the next question on the page. For every 1 unit increase in x, the y increases or decreases or is predicted to by this amount right here. In other words, if you sit a row further back, according to our line, it says that your score on the test is going to go about 1.1 points lower. Is that going to be super dead on for everybody? Very obviously not. Look at all these dots that are just way outside the pattern, but that's what our slope does tell us. The next thing I ask for is the correlation R. They don't tell you R straight up in this table, but they give you R squared, and that's almost as good. So for part C, what you're going to do is take these square roots, and you have to turn R squared into a decimal, which is 0.047. Don't ever do math on a percentage by itself. You always turn it to a decimal first. And if I do square root of 0.047, that is going to be 0.217-ish. Again, when you square root a decimal, it gets bigger. But this is a negative correlation. My slope is negative. If my slope is negative, R is also going to be negative. So make sure you have a negative sign on that value when you actually set it up. Okay, so finding R is not hard if they give you R squared. Next thing they ask for is if a line is an appropriate model. I talked about this earlier, and I've written this out several times, so I'm not going to write this one. But what I want to say about this is, again, this line isn't doing a great job. It's really not going to be super helpful with predictions, but the residual plot is randomly scattered. There's no leftover pattern. So a linear model is as good as anything for this problem here. So a linear model is as appropriate as anything because there's only random scatter in that. And then the last two things with this problem here are interpreting S and interpreting R squared. We've done this a lot, so I'm going to say it out loud, but I'm not going to write it down. You guys should probably try this for yourself before you listen to me, because we went over this in depth in the last video. So S, typical residual size. So basically, when we use row to predict score, or when we predict score based on row that you sit in, we can expect that our predictions from the LSRL will be off by about 10.06 points. That's a pretty big amount to be off by when you're making a prediction, okay? Our predictions are going to be off by over 10 on average because our line just isn't doing that good of a job. It's worth noting that my scale is only out of 100, so being off by 10 is a big deal. If I had like a problem where I was going by thousands or something like that, that same 10 wouldn't be such a big deal. So it's sort of relative to your data set, but being off by 10 percentage points is like a lot for this problem. So that's how you would interpret S. And you can look at your script from last lesson to write that out yourself. R squared, on the other hand, talks about the percent of the variability or the percent of variation accounted for by our line. So what I would say for that is that 4.7% of the variation in score is accounted for by the linear model relating score to row. In other words, out of all the different reasons why your score might change, why you might score higher or lower, did you study? Did you pay attention in class? Are you doing your homework, et cetera, et cetera? Apparently, our linear model dealt with 4.7% of the problem by like where you're sitting. That's a good conceptual way to think about it. So it's not surprising that it's a low quantity, given that the variable we chose was kind of weird. All right, so that is a good example of how you can incorporate these things to kind of paint a bigger picture of what's going on in the problem. This next slide right here isn't my favorite, if I'm being honest. It's getting a little bit more into just how you actually find that equation that the calculator gives to you. So you need to know these formulas are on your formula sheets, and you'll recognize that it's time to use them because you'll have like a little plug and chug style problem. So this is basically just going to be like algebra style. And I don't love it that this is like in the curriculum here, but let's at least talk through it real fast. So we already established in a couple of videos back that x bar comma y bar is on the least squares regression line. I showed you that in an example. So that means if I were to plug in to like a linear equation, a plus bx, I can plug in x bar and y bar for regular x and regular y. If you have y equals mx plus b, you can plug in an x and a y that are from the equation. So all they did is to find the y-intercepts right here, the second part. All they did is they isolated a in this problem. In other words, they subtracted the bx, the x bar, to the other side. So this is how you could calculate a, or the y-intercept, for the least squares regression line. Okay? The b part right here is for your slope. And to find slope, think about slope in general. It's delta y over delta x, change in y over change in x. If you ignore the r part for a second, s of y is the standard deviation of your y coordinates. So you have the change in y, s of y, how much your y is typically changed by, over the change in x. So to find this quantity for the slope of your line, it's basically a ratio of the standard deviation of y over standard deviation of x, but the points don't follow a perfect line. So to kind of account for that fact, you bring in the correlation coefficient and you multiply by that. That's a little bit of a hand-wavy explanation. Truthfully, I'm not going to emphasize this a lot in class, but what you'll need to be able to do is plug into a problem. They feel a little contrived sometimes, but like you see at the bottom right here. They just give you a bunch of information, and they say to calculate the equation of the LSRL for predicting fourth grade scores, for third grade scores. So the one you're predicting is y, and this is x right here. So the first thing I'm going to do is calculate the slope for my line. And the slope is going to equal, I take my r, which they say is 0.95, and I multiply that by the ratio of the standard deviations. The standard deviation for y, which is fourth grade, is 12.3. And the standard deviation for the third graders is 14.0. And all I'm going to do is just multiply that out. 0.95 times 12.3 divided by 14. And that gets me a 0.835 if I round. So the slope for my LSRL is about a 0.835. And then I'm going to use this guy right here to get A. So in order to do that, I'm just going to plug in, I think they tell me the average for the fourth graders, that's y bar, that's x bar right there. So it's really just kind of a plug and chug sort of a deal. A equals 55.1 minus, I just got B, and then I do my 61.7. And let me just type that guy in real fast and see what that equals. 3.58 is what I got. So you just use these little formulas. These are on your formula sheet, so you do not have to worry about memorizing them. And you're going to get that the least squares regression line, y hat, is 3.58 for your y-intercept plus 0.835x. And you can define x and define y. So they're plug and chug style problems. You'll see them on multiple choice questions every now and then, and it's just a matter of using your formula sheet and knowing that it's the time to do so. I care a lot more, though, about being able to take those pieces and understand them than to be able to use this right here. So it's something we needed to talk about, so you at least have the background for what is my calculator doing, but we're not going to be expected to do that too much in practice. Very last thing for this lesson is just a quick kind of reminder about just little mistakes that people make. And we talked about this already with R, but remember that switching x and y in a problem, it's going to change your equation. It's going to change how your picture looks. It's going to flip-flop things, and you're going to get a new LSRL. But R stays the same. If you switch x and y, everything changes but R. You will still have the same correlation. And finally, correlation and regression lines are only good for linear relationships. They are not a full picture by themselves. This is kind of a neat example over here on the side. You have 4 very different scatter plot problems. These 4 data sets look extremely different, but the R for each of these problems here is the same. R equals 0.816 for each of these problems here. So these 4 data sets that look extremely different all have the same R. So just because, oh, R is good, R is high, does not tell you the data set is linear. What's also interesting is these have the same line of best fit equation too. So these are really cool data sets here. All of these would have the same equation for your least squares regression line. So just because they give you a linear equation, just because they give you an R, doesn't mean it's the best choice and doesn't mean that your data set is linear. So be careful with that because it's really easy to go too fast and make that sort of an error.